A quantum computer is not just a faster computer. It's a machine that can solve problems that are completely intractable by any modern computer, no matter how powerful. But to really outperform a supercomputer, the quantum computer must be built using many quantum bits, or qubits, all individually controlled and coupled to each other in a large array.
Our team at UNSW has already established the record of performance for single qubits in the solid state. Our qubits are individual atoms of phosphorus implanted inside a silicon chip very similar to those that power all modern computers and smartphones. We've made qubits out of both the electron and the nucleus of the phosphorus atom. But because they are atomic-sized systems, you would normally need to place them a few atoms apart so that the electrons touch each other to perform quantum calculations.
We have now discovered that this is not necessary. We can make the phosphorus qubits talk to each other over much larger distances, at one condition, that we encode quantum information in the combined state of the electron and the nucleus. For example, we encode a 0 in the electron down nucleus up combination and a 1 in the electron up nucleus down.
We called it the flip-flop qubit. It is operated by pulling the electron away from the nucleus and then oscillating the electron position around its equilibrium point. This means that we can now control a qubit in silicon using electric instead of magnetic signals. This makes it much easier to integrate with normal electronic circuits.
And once the negative charge of the electron is pulled away from the positive charge of the nucleus, the qubit creates an electric field that reaches over large distances. So we can now design a large-scale quantum computer where there is plenty of space to insert interconnects, control lines, and readout devices, without having to fabricate components at the scale of a few atoms.
This is a major shift in the way we can build silicon quantum computers. Using flip-flop qubits instead of normal qubits will allow us to manufacture large arrays of qubits without having to push the limits of fabrication of conventional electronic devices. So it's a quicker and more economical way to build a quantum computer that is big enough to start having an impact in the world.